Okay, we continue. So the last topic which I would like to discuss is Green's functions in quantum field theory. And Green's functions actually is the most powerful tool for study quantum dynamics. And what I'm going to do, I'm going to derive representation for these Green's functions in terms of quantum fields in the interaction picture. Now, why Green's functions? That's because Green's functions, in fact, contain all information about quantum field theory. So in a way, the whole apparatus of quantum field theory can be reformulated at the level of these Green's functions, thus reducing the problem of describing interactions of quantum fields from operator language to functional language, to the language of functions. And in many cases, it's much more easier to deal with functions than to deal with unbounded operators acting in some Fock space or in some Hilbert space. So if you know all Green's functions of this series, then in fact you can say that this is the same as you know what your quantum field theory is. So Green's functions. And Green's functions. So my next goal is to derive the most important formula in quantum field theory, namely the formula due to Gell-Mann and law, which allows the computation of these Green's functions in perturbation theory. But first, the definition. Green's functions are defined in the following way. These are functions of n space-time points, so Gn, x1, x2, and so on, xn, which are given by the following expressions. So omega, t-ordered product of fields phi on x1, and so on, phi on xn, omega, where phi on x, here, this is capital phi on x, is the so-called Heisenberg field. Heisenberg field, which means the quantum field whose evolution is described by the actual interacting or full Hamiltonian of the quantum field theory. So the time dependence of this field is given by the following expression. So phi as a function of t and x is exponential I over h bar, the full Hamiltonian of the theory, phi evaluated at 0x, exponential minus I over h bar ht. The state omega is here the ground state of H. Ground state of the full Hamiltonian H. And it represents in this way the physical vacuum, which is assumed for me to be non-degenerate and normalized in the standard way to identity. So omega is equal to 1 and ground state of H, and this is a physical vacuum. This is not a vacuum of free fields. This is what is called physical vacuum. So by definition, Green's functions are expectation values over the physical vacuum of the time-ordered product of Heisenberg field operators. This is how they are defined. So my aim now is to somehow rewrite these Green's functions via quantum fields considered in the interaction picture, which means that these fields evolve with the help of free Hamiltonians. So these fields I will denote by small phi, depending on t and x, so also on time and x. And the evolution of these fields is defined by free Hamiltonian H0. And this is what we have also introduced before. Free field evolution. So these fields undergo free field evolution with a Hamiltonian H0. Now, the main idea which allows to relate the free fields and the Heisenberg field, which sometimes is called interacting or interpolating field, is borrowed from classical mechanics. When looking at a particle system momentarily, or if you wish, on a time slice, on just one time slice, you cannot actually understand whether its constituents interact or not. Now, imagine you have particles in the box, and you have a photo of this system, and somebody showed you this photo, and you look, so what you see are just particles at certain positions. How can you tell if they are interacting or not? There is no way you can answer this question. Either they are free or they are interacting. Because to understand if they are free or they are interacting, you need to somehow measure the influence, the correlation between these particles. And for that, you need time development. But if there is no time development, which is, and you have just static photo, then you cannot really say if particles are interacting or not. This gives an idea that actually at a given moment of time, say at time equals to 0, you can identify the free field phi 0x with a Heisenberg field phi 0x. Because you cannot say if this is an interacting field or this is a free field. But once you do that, then you see that the Heisenberg field, you can relate to the free field by the following formula. So you consider evolution in the following way. You write the evolution equation for the Heisenberg field in the following way. Phi on x exponential I h bar h0t exponential minus I of h bar ht. So this is clear what happens. So when you apply the free evolution operator to the field phi on x, you return back to phi 0x. To a free field at 0 moment of time. But this field coincides with the Heisenberg field at that moment of time. And then this Heisenberg field evolves as it should evolve with the help of the full Hamiltonian, right? So this is a formula which relates the Heisenberg field to a free field. At the one and the same moment of time. So both fields now are at the moment t, and then applying these exponentials from the left and from the right, you obtain the Heisenberg field at the same moment of time. Now, if you come back to, if you remember our discussion of scattering theory, there I introduced the evolution operator in the interaction picture, which looks like this, h0t1 exponential minus I of h bar, Hamiltonian t1 minus t2, like this, exponential minus I h bar h0 t1. And then you see that this relation between the Heisenberg field phi on x and the free field can be written with the help of this evolution operator in the following way: u0t phi on x ut0. So here is again free, and here is Heisenberg. And u0t is the Dirac evolution operator, which in full glory is given by this formula here. Thus, if you are now looking at T-ordered product of Heisenberg fields, phi on x1 and so on, phi on xn, you can rewrite this expression in terms of free fields and the evolution operators. So you get T-ordered product, and here you write u on 0 T1 free field on x1, u on T1 0. So that gives the Heisenberg field at the point x1. And then you do the same for every Heisenberg field under T-ordered product. So let's do it also for explicitly for T2, 0, T2, phi on x2, free field, u on T2, 0, and so on, and so on. So you make this substitution. So the last will be 0 Tn phi on xn, free field, u on Tn 0. And bracket is closed. Then you see that the Dirac operator satisfies the Markovian property, which we have discussed already, meaning that if you have this product, u on T1, 0, u 0, T2, then the resulting operator, the resulting product, does not depend on this intermediate moment 0. And so this is the same as u on T1, T2. Mm-hmm. This is the same as operator, say u on T1, T2, which actually allows me to write this expression in the following way. T-ordered product, u on 0 T1, phi on x1, u on T1, T2, free field phi on x2, and so on, and so on, and so on, up to u on Tn minus 1 Tn, phi on xn, free field, u on Tn 0. Now, again, using this Markovian property or group property of these operators u on 0 T1, I can write as u on 0 tau 1, u tau 1 T1, where tau 1 is some intermediate moment of time. And analogously, I can take u of Tn 0 and write it as a u Tn tau 2, u tau 2, 0, like this. And further on, since tau 1 and tau 2 are arbitrary, I can pick up tau 1 and tau 2 to be larger and respectively smaller than any of the moments of time T1 and so on Tn. So this means with this choice of tau 1, say, being bigger than any of the t's which is under the T-ordered product, and the tau 2 to be less than any of these t's under the time-ordered product, then I can do the following. I can write Gn, this Green's function, which I'm interested in, I can write it in the following form. Gn on x1 and so on xn is the following thing. Omega vacuum u on 0 tau 1. I take it out of the T-ordered product because tau 1 is larger than any of the t's which I have. And so under the t's, under the T-ordered product, as you know, all operators commute. And so that means I can write them in the following form. I can first write my free fields, and then I combine all t's, all u's which are standing in between phi's, and then they are combined in the operator, which is simply u, depending on tau 1, that's the initial point, and tau 2, this is a final point. And then there will be operator u on tau 2 0, which I took under, which I took away from the T-ordered product because tau 2 is the smallest value among all the times which I have. And then omega. But we know the expression for the operator tau 1, tau 2. We found it from the integral equation for operator, for the Dirac operator u. And it's given by the T-ordered exponent. But since I already have one T-ordered here, I can simply write this expression as omega u on 0 tau 1 T-ordered product of free fields phi 1 and so on, phi on xn. And this u on tau 1, tau 2, according to what we know about the Dirac operator, I write as the integral from tau 2 to tau 1. Sorry, tau 1 is the biggest time, tau 2 is the smallest time, dt v on t, where v is an interaction potential. Like this. Now, of course, you understand what I want to do. So the expression on the right-hand side depends not only on the points x1 and so on xn, but formally it depends on the points tau 1 and tau 2, although from these points nothing depends in reality, because it's the way we implemented this group property of operators tau 1 and tau 2. And so since nothing should depend on these times tau 1 and tau 2, what I would like to take is I would like to take tau 1 to plus infinity and tau 2 to minus infinity. Any questions here? Is this process of deriving the expression for the Green's function is clear? Does it make sense to you?
Yes.
Okay. Very good. So the idea is to get rid of the Heisenberg field, which is complicated interacting field driven by the full Hamiltonian, and somehow rewrite the whole Green's function in terms of free fields, which would make possible the explicit computation of these functions in perturbation theory. Now, typically, the Hamiltonian H0 has a continuous spectrum. Well, that's because it describes free particles. And the only normalizable state related to H0 is a vacuum state, is a vacuum of free fields. This state is normalizable. Typically, it's normalized. You can normalize it to 1. Now, on the contrary, if you talk about the Hamiltonian H, then this Hamiltonian might have a discrete spectrum of orthonormal eigenstates. I denote this by omega n. No, because it's a Hamiltonian of the full theory, and we know that in the full Hilbert space there could be normalizable eigenstates of H, for instance, those corresponding to bound states. And these states are eigenstates. I assume that they might exist, and they are eigenstates of H with eigenvalues given by energies En. So there is a certain set of energies which I assume to be positive, related to H, and E0 then and correspond to the energy of the ground state, and the corresponding ground state I denote by omega 0, and this is the same as my physical vacuum, which I introduced in the definition of the Green's functions. Actually, it is always convenient to choose E0 to be just 0. So ground state energy is 0. Now, the vacuum, which is the only normalizable state in the Hilbert space, is free vacuum. Since it's normalizable, it can be expanded over the eigenstates of the discrete spectrum of H. So in other words, this free vacuum is sum from 0 to infinity Cn omega n. Where this coefficient Cn you can then find as overlaps of eigenstates of the full Hamiltonian with the free vacuum. So that's the way how you can restore the coefficients in this expansion. Now, if you consider the application of this operator U on 0 tau to the free vacuum, I take it acting on the free vacuum, then you can do the following. First, you write the definition of what is this U. So I over H bar H tau exponential minus I over H bar H0 tau acting on a free vacuum. Then you know that this is a free Hamiltonian acting on the vacuum. So H0 acting on a vacuum produce 0. And so you will be left over with just exponential containing the full Hamiltonian acting on free vacuum. But this now you substitute for its expansion. So sum n equals 0 infinity Cn omega n. And you can pick up, you can separate from this infinite sum the contribution of the ground state. And the ground state is, what is this? It will be C0 exponential I over H bar H, which I replace for E0 tau acting on omega 0, plus the rest. And the rest will be sum from 1 to infinity Cn exponential I over H bar En tau acting on omega n, right? So now I use the fact that all these states omega n are eigenstates of the full Hamiltonian. And since we assume that the ground state energy of the physical vacuum is 0, then this becomes C0 multiplied by omega 0 plus infinite sum from 1 to infinity Cn exponential I over H bar En tau acting on omega n. This is how it looks like. Now, there is here one trick, which I'm doing here, not how to say, which I do here pretty roughly, but there is justification to it. Namely, what I would do, I would take the limit on both sides of this expression when tau goes to plus or minus infinity. So when tau goes to plus minus infinity, I would like to take a limit of this expression. So the first term just remains, nothing happened to it. And here there is a limit tau going to plus minus infinity, sum 1 to infinity Cn exponential I over h bar En tau multiplied by omega n. Now, when you take this limit tau to infinity, these exponentials become highly oscillating factors. So they highly oscillate. And then in mathematical analysis, there is a so-called Riemann-Lebesgue lemma. Riemann-Lebesgue lemma, which tells that if you consider these exponentials, these highly exponential oscillation functions as generalized functions, not as the usual functions, but as generalized functions or distributions, which actually what you should do in quantum field theory. Then, because of these high oscillations, the corresponding contributions produced by these generalized functions in the limit tau going to plus minus infinity, they vanish. And because of this vanishing, you can say that these limits are actually reduced just to C0 acting on the ground state omega 0, so C0 acting on the ground state omega. Or if you use the property of the operator U, that this is the same as U minus 1 on tau, U minus 1 on tau 0, yes, U minus 1 on tau 0, then multiplying both sides, then substituting this for U minus 1 tau 0, you can rewrite this formula also in this way as lim tau going to plus minus infinity, U on tau 0 acting on omega, so on the other side, has been given by 1 divided by C0 multiplied by omega, multiplied by vacuum of the free theory, sorry. And analogously, lim tau plus minus infinity, left vacuum, U on 0 tau equals to 1 divided by C0 star. C0 can be a complex number, so C0 star multiplied by bra vacuum. And this is just the second expression is just a conjugate, a Hermitian conjugate of the first one. Moreover, you also know that the vacuum expectation of the S matrix can be written in the following way. We know that S matrix is a double limit tau 1 to plus infinity, tau 2 to minus infinity of the product of Dirac evolution operators, which can be written in the following form, like this. So if you multiply these operators, this is the same as U on tau 1 comma tau 2. And the double operator limit, tau 1 going to plus infinity, tau 2 going to minus infinity, gives you S matrix. So the vacuum expectation value of the S matrix then according to what we have just obtained, then is given by the expression. Here we look at these expressions, we see that this is nothing else as modulus of C0 squared omega scalar product of omega with itself, which is actually due to normalization of the full vacuum, of the physical vacuum, is just modulus of C0 squared. Therefore, if you now return to our expression here and take the limits tau 1 to plus infinity, tau 2 to minus infinity, and look and basically substitute the actions of this limiting evolution operators on the physical vacuum, we can replace it by the free vacuum. And there appears C0 squared. In this case, there will appear modulus of C0 squared in the denominator. But this modulus of C0 squared is, as we know, simply the vacuum expectation value of the S matrix. And therefore, the Green's function takes the following form, where all fields now standing in this expression are just free fields. Here I write it as an integral over time of V on T. Vacuum of a free theory for free fields. Naturally, we have now vacuum of a free theory. And in the denominator, we have a vacuum expectation value of the S matrix. And we know what is S matrix. If you remember, then you know that this is nothing as a T-ordered product dTV on T. And so this is what is called Gell-Mann law formula. Gell-Mann law formula, which gives the free, which gives the Green's function for Heisenberg fields in terms of free fields. Gell-Mann law formula. This is one of the basic formulas in quantum field theory, because it allows the computation of Green's functions of Heisenberg fields, which encode the full information about quantum field theory, where free fields via T-ordered product of free fields, and the potential V on T, where evolution of V on T goes according again to the free dynamics. Sometimes people distinguish between normalized Green's functions and unnormalized Green's functions. And you see that this Green's function, this which we obtain in this way, is normalized in a sense that if there is no insertion of fields phi on x1 and so on phi on xn, then G0, when there are no insertions, it's simply the ratio of vacuum expectation values of this matrix, and therefore it is 1. And so Gn is called Green's functions. Green's function, this is definition, is Green's function, Green's function without vacuum loops. And this is something which I will explain a little bit later in the next lecture, why it maybe even in this lecture, why this is called Green's function without vacuum loops. Because we can also introduce a Green's function with loops. This Green's function, and so on, xn, is understood as the same as Gn, but without denominator. It is simply given by this expression without insertion of the denominator, and this is called Green's function with vacuum loops. Mainly, people work with normalized Green's functions, so with Green's functions without vacuum loops, because vacuum loops do not produce contribution into the scattering process. If you start computing various scattering process by using Green's functions, and these contributions related to vacuum loops, they should be discarded, and the way to discard them universally is just to work with the normalized Green's function, which excludes the so-called vacuum loops. So vacuum loops, these are Feynman diagrams. They correspond to Feynman diagrams where you don't have external legs at all. No external legs, no incoming and outgoing particles. This is some internal loops where particles are created from the vacuum and disappear in the vacuum. And so they never scatter in this way. Any questions here? So this is one of the most important formulas of quantum field theory. Of course, there is a number of paradoxes which are related to this formula and which puzzle people for a long time and still continue to puzzle people about this formula. And this because the starting point for our perturbative computation was a formula based on interaction picture and the unitary transformation, which relates the Heisenberg operators and interaction and the free fields. But there is a famous theorem of Haag, which states that such a unitary equivalence is in fact deceptive and wrong, and it can never be really achieved in infinite volume continuum quantum field theory. Because if you really assume the validity of this interaction picture, then you can come to paradoxical conclusions, like, for instance, that correlation functions of free fields and interacting fields are the same, which of course cannot be the case. And the reason, I mean, I don't go too much to the explanation of why this kind of things arise, but one of the deep reasons behind this result is that in systems with infinite number of degrees of freedom, of which quantum field theory is, there exist unitary inequivalent representations of the fundamental commutation relations. Inequivalent representations, which is, of course, in a very sharp contrast with a standard Stone von Neumann theorem, you know, from quantum mechanics, where the theorem says that up to unitary equivalence, there is a unique representation of the fundamental commutation relations, of the Heisenberg commutation relations. So in quantum field theory, this is not so. And this is a deep reason why these paradoxical results that interacting fields and free fields might have the same correlation functions arise. Now, this formula by Gell-Mann and Lowe is correct, although its derivation, which I have presented, has problems. And I'm not going to hide this, that there are problems. This is because all my derivations I did here, they're pretty formal. Pretty formal in a sense that if you want really to follow all the steps in a rigorously, in a rigorous mathematical way, then first you have to start from a theory which is regularized both in the ultraviolet and the infrared. In particular, this infrared regularization means that you have to deal with a theory in finite volume. So you have to put your theory in the box. And this regularization reduces the number of degrees of freedom to finite quantity. So it becomes finite. And therefore, in this case, the Stone von Neumann theorem becomes applicable. Now, of course, at the end of calculations, you have to worry about taking the continuum limit and also about a restoration of Poincare invariance, because as soon as you put your system in a finite box, you break Lorentz invariance. And so to speak, the numerator and denominator in this Gell-Mann law formula, they both have problems. But somehow these problems miraculously happen if you put these things under ratio. And so in this respect, you can show that the mathematically, how to say, rigorous and impeccable derivation goes through, and at the end, you get this Gell-Mann law formula, which can be further used for computing the correlation functions in quantum field theory.
Here the numerator and denominator separately are not Lorentz invariant.
No, they are. But if you do the theory in the finite volume, then they are not. But why you have to do things in the finite volume? Because typically, the integrals that arise on the way, they are divergent either in the infrared or in the ultraviolet. So ultraviolet regularizations, you cut off, you take care by cutting off momentum, and infrared regularizations you can overcome by putting system in a finite box. But you break in this case the Lorentz invariance. So my derivation is heuristic here. I don't pretend that this is a rigorous mathematical derivation I'm doing here. I just warn you that this formula is by no means trivial. So this derivation, although it looks rather straightforward, but I want to say that it's only heuristic. And the rigorous derivation requires much more work that has been done so far. But for our practical purpose, this derivation is enough. At least now you know what is the Gell-Mann law formula. There is a lot of discussion in the literature. I can refer to some books where this formula is discussed, and the conceptual foundations behind this formula are discussed as well at length. So you can look in there to see what people will say about this formula. In any case, for us, it is important now that we know it, and we want to somehow work with this formula in practice. We want to understand this formula, how to apply it. And it is very convenient to deal with all Green's functions at once by introducing the corresponding generating functionals or functional. And this is done in the following way. I introduce the classical function.
Professor.
Yeah.
So there is something called means. Am I right that this is something called like this is being regularized by something called like Pauli-Villard's regularization?
Yeah. So this correlation functions might have divergences, and they do have divergences, which you need to regularize. So written in this way, you can have infinity in the numerator, you can have infinity in the denominator. And so the question is how you cancel these infinities. And that involves the regularization procedure, and regularization can be done, for instance, by Pauli-Villars, or it can be done by high derivative terms, or it can be done by what is called differential regularization. There is a number of ways how to deal with this problem of divergences. But you're right, yes, that's a part of the problem. That's what I refer to as ultraviolet divergences. Yes.
Okay.
So you introduce a classical function, j on x, which you don't specify, but you simply keep it as an auxiliary classical variable. So it's not a quantum thing, it's just some classical variable. Usually it's called an external source. An external source. And with this external source, you introduce such a functional of this source. It's called z on j, which is an infinite sum from 0 to infinity, in divided by n factorial, integral dx1 and so on, dxn, correlation function jn depending on x1 and so on xn, j on x1 and so on j on xn. You introduce such z on j, and now if you want to compute it, you can do the following. So first, you consider the instead of gn here, you substitute its numerator. So you say that this is 0 phi t ordered product, phi on x1 and so on, phi on xn, like this. Then there is this exponential minus I of h bar, integral minus plus infinity v on t dt, and then vacuum, and then you have this source terms j on xn, and you see that these source terms, because they are classical, they are purely classical, you can take them inside the t ordered product, and you can also take inside the t ordered product the integrations. So integrations over x1 and over xn, because t ordered product in each term will rearrange these phi's in the right order. And then summing up this expression, you will simply see that let's not call it z, let's call it z curly, because I'm actually substituting here not gn for the moment, but just the numerator of gn. So I substitute here this expression. Okay, I substitute then this expression, and then I combine each phi on x1 with a corresponding source term. So I bring phi on x1 close, and I bring the corresponding integration close to the corresponding phi. And then what I see, I'm getting here simply the following expression. So infinite sum n0 infinity in n factorial. Vacuum expectation value I can also take out of the sum and have it somewhere here. And then t ordered product also can be taken out. And here you will get integral phi on x1, j on x1, dx1, integral phi on xn, j on xn, dxn. Then substitution of this exponential. And the vacuum. Oh, this expression. But then you see that each of these integrals is one and the same expression, right? Because you're integrating over x's. So that's the one and the same expression. And this means that actually what I have here is the one and the same integral, which is integral over fxj on x dx in the power n, right? In the power n. So the same integral appears n times. But then what is written down here is infinite sum, which is nothing else as an expansion of exponent, because it's I in the power n divided by n factorial. So this means that the whole thing can be written as a t-ordered product of what? Of exponential I, it's coming from this I here, integral phi on x j on x dx multiply with exponential minus I over h bar integral from minus to plus infinity v on t dt a vacuum. Okay, that's very interesting. Now, then it is convenient to introduce a concise notation. This is what people usually use in order not to write these long formulas and integrals. So this integral, this is usually denoted as I j dot phi. So which means exactly what is written down here. So integral of phi on x j on x dx and I, yes, I. While this term here, minus v on t dt, integral from minus to plus infinity, this is nothing else as interaction part of the action. So this part with the minus sign is simply as int, interaction part of the action, considered as a functional of free fields, because this v on t is the potential of interaction just written in terms of free fields. So it's a functional of phi. And therefore, the whole thing then becomes nothing else as compactly written expression, which involves t-ordered product of exponential I over h bar as interaction, depending on phi, plus I j phi. And bracket is closed. And now you see that the expression in the denominator of the Green's function does not contain fields phi. And sorry, it does not contain j, it does not contain source, it's just the same expression where j is put to 0, which basically tells you that the generating functional for the Green's functions, which is now introduced as I have written before, gn on x1 and so on xn, and then j on x1, j on xn becomes, according to this formula, simply the ratio of t exponential I over h bar as int phi plus I j phi, vacuum is closed, divided by the same expression where you put j is equal to 0. So this is simply the same thing. I can write j dot phi, but then at the end of the computation, if this is the same function as numerator, you put it in the denominator, but you put j is equal to 0. Now, why this generating functional is convenient? Then it is convenient for a simple reason that if you want from this generating function to get the individual Green's function, then it's very easy. All what you have to do is to differentiate n times with respect to the source, and then at the end put the source to 0. So Green's function is obtained as a variational derivative of the functional z on j with respect to the source. You take z on j, differentiate it in times over j on x1 and so on j on xn, and that at the end you put j to 0 and you get your Green's function. So this means you don't need to consider these Green's functions individually. You can compute all of them at once if you compute this quantity z on j. That's why z on j is very important. And this is a nice representation, functional representation for this quantity. And this is not the end of the story. There is even further super nice development, which consists in the following. Actually, we have a weak theorem at our disposal, and we know that applying the weak theorem means that we need to take all the parents of fields, and this can be super nicely done with the help of the exponential operator, which I introduced in the previous lecture. This tells that t-ordered product of such a thing as I over h bar s int interaction phi plus I j phi can be computed as a normal ordered product of these fields acted with an operator 1 over 2 delta delta phi, Feynman propagator delta delta phi, acted on this exponential I over h bar s int phi plus I j phi, right? We have already discussed that in this representation, you first consider field phi as a classical field, you act with this operator, and then at the end, you make field phi again, the quantum field, and all under the sign of normal ordered product. Moreover, if you put at the end this t-ordered product in this vacuum expectation value of the free vacuum, all fields which are not paired, will produce zero contribution, right? And this means that since evaluation of the vacuum expectation value of the normal ordered product of any functional of phi yields the value of this functional at phi is equal to 0, then you can say that all what you have to do is then evaluate this expression, apply this operator to exponential I h bar s interaction phi plus I j phi, and at the end put this field phi to 0. Because if the field phi will be left over under the sign of the normal ordered product, it means that it contains creation annihilation operators. And if you then put vacuum on the left and vacuum on the right, then any expression which is left over with the field phi will vanish in this vacuum expectation value. In other words, this is equivalent to say that you can compute this variational derivative, variational operator, and then you put phi to 0, and this is exactly the contribution you are looking for, namely time moderate product of T operator of exponential I h bar as int plus ij phi. That's exactly the contribution you are interested in. Is this idea clear? You apply this operator and then you put at the end phi to 0, and this is already the vacuum expectation value of the T ordered product you are interested in. Moreover, there is another super nice thing, is that actually this expression I over h bar as int phi, you can split exponentials like this, as fields phi commute, j is classical, so this is the same. And you can rewrite it in the following way. So the result of having field phi in S interaction can be sort of obtained in the following way. You replace in S interaction term the field phi by the functional derivative 1 over I delta over delta j. So instead of field phi, you substitute such an operator, which acts then on this exponential j phi. Now, what is a nice feature? You see, if you expand this exponential into series and you start applying S interaction with this operator 1 over I delta delta j to this operator, since derivative of the exponential is exponential again, every time you act with such an operator, exponential will be reproduced. And every time you differentiate, you take the functional derivative of the expression which is in the exponential, so you differentiate 1 over I delta delta j, the field phi will appear and will replace this 1 over I delta delta j. You see, this is clear. You differentiate exponential, you will get exponential back. And instead of 1 over I delta delta j, you will be receiving field phi. And so you will be returning back exactly to this expression you start with. Furthermore, now you have this operator standing first. Then we agreed that we can write as interaction term depending on the functional derivative. Differentiation over phi and differentiation over the source, they commute because these are completely independent fields. And therefore, you can take S interaction, this term which depends on S interaction, to be the first one and act with this exponential on ij phi. And this action can be elementary computed because, well, you can compute, and in the end, you are interested in the result where you put phi is equal to 0. So this expression then must depend completely on j because you put phi is equal to 0. But again, it's clear what happens. Every time you differentiate over phi exponential, you will reproduce the same exponential, and field phi will be replaced by ij. So at the end, instead of this, you will get, instead of this exponential, you will get minus 1/2 j delta j, where delta is a Feynman propagator, and this j delta j, since this is a function, this is a functional form for integral dx dy j on x delta x minus y j on y. You will be also left with exponential ij phi, but then you put phi to 0 and this exponent disappear. And so the final upshot of this procedure is that we have reduced the derivation of the generating functional for Green's functions for without vacuum loops to the following super nice formula: exponential I over h bar, interaction term in the Lagrangian, depending on the variational derivative as an argument, applied to the term which depends on the source and the Feynman propagator, J delta J. And then in the denominator, we have to do absolutely the same. So it's the same expression as in the numerator, except that at the end of the computation, we have to put in the denominator J to 0. And this is a very general formula, very important formula, which leads to practical determination of all Green's functions in quantum field theory. Any questions? So once this Z on J is found, you can compute Green's functions. You can compute Green's functions by using this formula here. So with this, I would like probably to finish. So next Friday, we will have our two last lectures, where I will develop the formalism of Green's functions and generating functional for Green's functions further, and show you some features, some outcome in application of these nice and general formulas to the case of phi-4 theory. Okay. If you have any questions, you can ask me.
Professor, so here is ZJ here is for general fields or for just for scalar fields?
Well, this is I introduced for scalar fields, but in fact, this Gell-Mann law formula is general. So under the T-ordered product, you can put any fields which you have in your theory. This could be fermions, that could be electromagnetic fields. So this is a very general formula, very general derivation.
Okay.
You just need to adjust the corresponding source. For instance, if you put just fermions inside the ordered product, then your source must also be element of what is called element of a Grassmann algebra. But otherwise, it is very, very similar. So all the computations leading to the generating function will go through. I just demonstrated for simplicity for the case of a scalar field, because it allows me to pass all the steps in a very explicit way. But of course, this derivation is not restricted just to scalar fields. No, by no means. It's a general thing.
Yeah.
Mm-hmm. You see, everything, we don't have any more operators. No operators at all. All info we have is a Feynman propagator here and S interaction. So interaction part of the action. Then this is now functional analysis to accurately perform all the operations of taking the variations and computation of the integrals which appear from the expansion of S interaction. No operators anymore. All operators are gone. Yeah, there was a question.
Professor, when you prove at the middle of the class that the frequency of the scattered photons is also lower than the frequency of the incident photon. I was thinking something. My question is, can we have equilibrium, thermodynamic equilibrium of electrons and photons? Because imagine if we have thermodynamic equilibrium, then during scattering, the photons are transferring energy to electrons continuously. Then I don't understand then how can have equilibrium, thermodynamic equilibrium between electrons and photons during scattering.
Yeah, do you see the questions you ask actually go outside the quantum field theory, because of course, the point is that you can have the thermodynamic equilibrium, and this is the one which you study in statistical mechanics under the name black body radiation. This is what it is.
Yes.
That is black body radiation. And this is the situation where electromagnetic waves in the cave are in the thermodynamic equilibrium. And this is due to the fact of interacting of these electromagnetic waves with the oscillators, say, built up or sitting in the walls of this cave. So there is a constant process of electromagnetic wave exciting the oscillator, and for oscillator emitting radiation back, such that sooner or later in the cave one finds in the thermodynamic equilibrium. If you don't do anything on this system and wait quite enough, then, as you know, in statistical mechanics, equilibrium statistical mechanics, the state of equilibrium will be reached.
Okay. Yes, I was thinking, because for me the contradiction was that each time the photon scatters, he loses his energy. Then we have like a transfer of energy from photons to electrons. Then this is not the equilibrium state. But I was thinking that maybe if this continues, you will produce positrons, and then with this positron you can create again photons. But okay, so we can have equilibrium. So
no, you can have an equilibrium. There is no problem. This is your electron receives actually more energy in the scattering process because electron gets energy, and if electron gets energy, it moves faster. There could be other collisions of electron with other electrons in the wall, and so that induce radiation back, and so on and so forth. So there is a back reaction from the stuff back into the radiation.
Okay, thank you.
So at the end of the day, yes, there will be a certain temperature of black body radiation. There will be Planck's distribution of the energies over frequencies. No, and all this what you learn from statistical mechanics.
Okay, thank you.
What we are talking here, I mean, in this case of quantum field theory, this is just a single act of interacting a single electron with a single photon. But then this procedure, I mean, this process, which is encoded in the microscopic Lagrangian, is dressed by the notion of d-ellipse, Lorentz invariant phase space, where we say that actually we cannot observe the individual act in our device. It's just impossible to have just one photon, but what we observe are outcoming particles in a certain range of momenta, and that introduces all these, how to say, factors which actually make a difference between scattering amplitude and the cross section. You see, this cross section is a thing which is defined by scattering amplitude, and it's also depends on this Lorentz invariant phase space, so to speak.
Yes.
So it's not only the amplitude which defines this process. You see, the important point is that if there would not be electrons and would be just photons, then equilibrium is not possible, because, I mean, photons, they never interact with each other. The interaction of photons with each other, this is a very highly suppressed effect, because for that you need to polarize vacuum and so on and so forth. If you don't go to that extreme, photons could not reach equilibrium without having matter, without having electrons or positrons. And if you study this black body radiation process, then in the original Planck's idea, Planck said that in order to reach for photons a thermodynamic equilibrium, you need to add to this system just one small piece of dust. This is how he called it. A piece of dust, a small piece of dust, a small piece of matter, such that the electromagnetic waves start to talk to matter. And this is because of that thermodynamic equilibrium is achieved. You may not introduce this dust, and this is what is done in the books, in the modern books on statistical mechanics. People simply say about the cavity, cave in which your radiation is confined, and then the role of this dust is played by the walls of this cavity, which are material walls containing oscillators.
I understand, Professor, very interesting. But then it means that we can have equilibrium with light and only electrons. We don't need positrons for this. But
no, we don't need positrons. No.
Oh,
electrons
okay.
are enough. They interact with light, so yeah, that's fine.
And from the point of view of quantum electrodynamics, what is the process that an electron emits a photon? Because we need this back reaction. What is the process? This process that an electron emits a photon.
No, this is a process which we have just seen. For that, you need this interaction term psi bar gamma mu psi a mu. This is what we have seen. So such process is impossible, that you have just photon and then you get electron coming out of it. That's not possible. There is no such interaction vertex in the quantum electrodynamics. This is not possible. There is no such interaction term. What is there is this process, where you have photon coming in, and then there is electron coming in, and electron or positron you getting out. And this interaction vertex is described exactly by this gamma mu psi bar psi a mu. So this is a mu coming in, and this is a psi, and this is psi bar coming out.
Okay, perfect. So here the electron.
And if you want to describe polarization of vacuum, then you can have such a diagram. Say, for instance, photon, propagator, photon. But then this is a loop effect. like this. And this process, I think I also discussed in the lecture notes. Let's see, it's called pair annihilation, but I do it in a different way. I do it in an opposite way. So in a way, I say I have electrons and positrons, electron plus positron getting in, and the gamma quanta coming out.
Yes, true, but for this we need positrons. Only for electrons it's possible.
Yeah, we need positrons to get these photons, because otherwise this process will not be compatible with the conservation of electric charge, because electric charge on the right hand side is 0. Photons are not charged with respect to themselves. You see, this is neutral system because it's an electron and positron, and this is neutral system. Gamma to gamma. Okay?
Oh, okay,
I think this is important. This is important. So we cannot break the conservation laws.
Yes, I understand. But then without positrons, how we can
This is this
restore
process here.
the energy of the photon?
Sorry?
I understand, but if we don't have antiparticles, then how we can restore the energy that the photons lost during the scattering?
But positrons are there, so I don't quite understand your question. Positrons are there, so this is an effect of annihilating of electron and positron. So electron and positron do disappear, but as a result, you get two photons getting out. Say this is will be electron, this will be positron, and this is a diagram at tree level which describes this process.
No, yes, I understand in this case, but my original question was only electrons on photons. How you can produce more photons, because the photons lose their energy during collisions. Then you need something that
why not? You have an electron and a photon, and then at the end you have an electron and a photon, and there is an exchange of energy. So conservation laws is preserved. Nothing prevents this process because charge is also preserved. I don't see any problem with this. No, photon is red-shifted, electron gets energy. The conservation law is fulfilled. That is what I implemented in these formulas. You don't need, say, a positron for this process.
Okay.
Yeah, so this is, if you wish, in classics, it's what I call Thomson scattering. You have an electron, it comes electromagnetic wave, it becomes oscillate, it become to oscillate, and then it emits photons again. This is this process.
Yes, I understand, Professor, but from the point of view of, I think, the second law of thermodynamics, I think the entropy is if you analyze in time what happened, the photons are losing energy.
you cannot first of all, photon loses energy, but electron get more energy, right?
Yes. Then this.
And so once again, this is not a thermodynamic process which you are discussing. It's a one event, one collision event, which happens, but in a way, to keep a thermodynamic equilibrium, you need, in a way, to keep the constant exchange between electromagnetic waves and the walls of cavity, right? It's
Yes.
not just one event which happens. This collision happens, and so and then things stop. No. Moreover, what you're talking about there is a statistical system. So you must have a very large number of particles, and actually the thermodynamic limit is taken when the number of particles tends to infinity, right?
Yes, yes.
So
No, yes. Thank you, Professor. No, yes. My
Mhm.
question was about this, a system, but I think I understand it. Thank you.
Okay, okay. Okay, if you don't have any further questions, then on Friday we will have our last 2 lectures where I try to explain more about the construction of the correlation functions. Okay?
Okay,
Okay,
thank you
sir.
very much.
Okay, then
Thank
I wish you a pleasant day and till Friday. Bye-bye.